In this specific lesson, we're going to look at combining Newton's first law with Newton's second law in order to study cases of equilibrium, specifically static and dynamic equilibrium. So what is equilibrium? So if we look at this box right here, it's a very simple box. So very simple, perhaps deceptively simple. We can see that we have 30 newtons acting towards the right and 30 newtons acting towards the left. Thus, the net force in the x direction is 0. We can also see in the y direction we have 50 newtons acting upwards and 50 newtons acting downwards. Thus, the net force in the y direction is also 0. So these cases where all the forces are balanced and the net force in both the x and y direction are equal to 0 are what we call equilibrium. So the box right here would be in a equilibrium condition. So equilibrium means that the net force on the object is 0 in all directions. Hence why we call it equilibrium. Equilibrium means balanced. No net force means no acceleration. So as a result, we have a case, if we recall Newton's first law, we have a case where no net force means no acceleration. Hence equilibrium means we're either at rest or moving at a constant velocity through Newton's first law. So the first type of equilibrium is known as what's called static equilibrium. Static meaning not moving. So the object, in this case, the object is at rest and net force acting on the object is 0. Dynamic equilibrium refers to the second case in Newton's first law where object moves at a constant velocity and no net force acts. So dynamic equilibrium describes, as I just stated, an object moves at a constant velocity and has a net force acting on it of 0. Our conditions, as we just talked about, is that the net force in both directions, x and y, must be equal to 0. Remember again that we must treat the x and y directions separately. So we must check for 0 net force in the x direction, 0 net force in the y direction. If either one of these conditions is not met, say our net force in the y direction is 0, but our net force in the x direction is not, then our object is not in equilibrium. So summary of equilibrium conditions. So here are some keywords to watch out for in terms of problem solving. Okay, we have static equilibrium, which means at rest or stationary. So you need to watch out for those keywords, at rest or stationary, which means our velocity is 0. And for static equilibrium, our acceleration is 0. For dynamic equilibrium, dynamic referring to something that's moving, you need to watch out for the keywords of constant velocity or constant speed, which implies our velocity is, well, constant. Yeah, nothing really too much to it there. So in that case, our acceleration is also 0 in dynamic equilibrium, but we're moving at a constant velocity or constant speed. So those are the keywords you need to watch out for specifically in problems. So in terms of solving equilibrium problems, the problem-solving process is mainly the same as before, as with free body diagrams and what we covered in 2.1, but we have a slight modification. So we go about our problem solving as usual. We draw a free body diagram representing the forces acting on our object. We identify what the problem is asking for you to solve, an acceleration or a particular force. And then our third step, the slight modification we make, is we need to determine if the system is in equilibrium. So again, if you see those keywords at rest or stationary or constant speed or constant velocity, that indicates to you that you're at equilibrium. And hence you're sure as heck not going to be solving for acceleration since that's going to be 0, and hence implies that your net force is acting on your object is 0. You're going to sum the forces in the x and y direction separately. Again, remember, please, I can't emphasize this enough, that they must be solved, that the forces must be summed separately. They're independent. And then you solve for your unknown quantity. So let's look at an example here. A hammock consisting of two identical straps right here is used to support a 50 kilogram mass. This is a very blocky hammock here. It doesn't look too comfortable to lie in. When the mass is loaded, the straps make a 30-degree angle with the ground, as we can see right here. We're asked to find what is the tension in these straps. So again, we start as usual. We draw a free body diagram. We know we have tension acting at an angle in each of the straps. We know we have the force of gravity that's pulling down on our hammock. We do not have a normal force here since the hammock is not in contact with another surface. In step 2, we're asked to identify the tension T in the ropes. Now, in this specific case, and this is because this is a problem that I created, there isn't any indication of at rest or constant velocity, but hammocks are at rest. They just kind of sit there. So even though it's not explicitly stated, in this case, it's implicitly stated. It's implied. So the system is in equilibrium, which implies our horizontal acceleration and our vertical acceleration is 0. In step 4 now, we need to break up tension to x and y components. Remember that if a force acts at an angle, we must break it up into x and y components. So our tension acting angle, we can break up into Tx and Ty. For the tension on the right side, Tx will act towards the right, and the tension and the vertical tension will act upwards, whereas for the left side, Tx, the horizontal tension will act towards the left, and the vertical tension will still act upwards. So Tx, if we apply trigonometry, is going to be T cosine theta, and Ty is going to be T sine of theta. So now we sum our forces in the x and y direction separately. We're not going to sub in trigonometry yet. We're just going to use Tx and Ty. So in the x direction, we have Tx minus Tx equals 0 newtons. Again, the horizontal tension on the right side acts towards the right, and on the left side, it acts towards the left. So we have Tx minus Tx equals 0 newtons. And hence, this is not really useful here because, well, we don't really have anything to work with here. Tx and Tx are going to cancel out in this case. So in the x direction, we're without a paddle right now. So let's go to y direction to see what we have. So in the y direction, we have Ty plus Ty minus Fg equals 0 newtons. So again, the force through gravity acts down, and both vertical components of tension of both straps act upwards. So we have Ty plus Ty, or 2Ty minus Fg equals 0 newtons. So in the y direction, we're going to have 2Ty minus Fg equals 0 newtons. We can now substitute in the trigonometric expressions. 2 times T sine theta minus Fg equals 0 newtons. Or solving for T, we're going to get T equals Fg divided by 2 sine theta. Now we can replace Fg with the equation for the force due to gravity, mass times the acceleration due to gravity, divided by 2 sine theta, where now if we plug in all of our known information, the 50 kilogram mass, the 30 degrees, and the acceleration due to gravity, that's going to yield for us that our tension must be 500 newtons in each strap. And thus, this is the basic setup for an equilibrium problem. Again, we need to make sure we follow these steps as they do keep us organized, as physics problems can be quite tricky. So next we look at air resistance and drag, just from a conceptual standpoint, not from a mathematical standpoint. So the force of drag, or air resistance, or really any type of resistance to a fluid, say like you're swimming in a pool, is what we call a retarding force, a force which acts opposite to direction of motion. Friction itself is also a retarding force, but it's also known as a dissipative force as well. So force of drag is either retarding or dissipative force, a force which acts opposite to the direction of motion. It occurs as a result of air molecules colliding with an object, the same way that friction occurs due to the molecules between two surfaces colliding, the roughness of two surfaces colliding. So there are two factors that affect drag. The surface area of an object, so the more surface area than that object has, let's just say that and not then, the more air molecules will collide with it, which we see right here. Bowling ball tends to have a small surface area of contact than, say, a feather or a piece of paper, so there's going to be more air molecules colliding with a feather than with a bowling ball. Hence why when we do account for air resistance, a feather will fall at a slower rate than a bowling ball because the feather has more air resistance acting on it. And then also the speed of an object. The higher the speed, the more frequent the collisions with air molecules will be. You can see this if you've ever stuck your hand out a window or you've ever been on a roller coaster. The faster you go, the more you feel the wind in your face, thus indicating that there is more air resistance acting the faster you move. Terminal velocity, so now we apply these conditions that we've learned about for air resistance to equilibrium. So when the force due to air resistance is equal and opposite to the force of gravity, what we call that is a dynamic equilibrium case, and we call the subsequent velocity of our object in that case the terminal velocity. So terminal velocity refers to the maximum speed a falling object will reach when it is in a state of dynamic equilibrium. So air resistance acts equal but opposite to the force of gravity. The idea being is that as your object falls and speeds up, the force of air resistance will increase because your object is speeding up. So you will eventually reach a point where the force due to air resistance is equal in strength but opposite in direction to your force due to gravity, and hence you will be in a state of dynamic equilibrium. As a result, terminal velocity is the maximum speed, and your falling object can never exceed this maximum speed. The terminal velocity for different objects, for every object, is different, but we will not look at in this class as it involves the use of calculus.